Tree recursion, when functions call themselves twice. Regular recursion calls itself once, a nice linear chain. But what happens when a function calls itself 2 times? Things get wild. The classic example, Fibonacci. Each number is the sum of the 2 before it. 0, 1, 1, 2, 3, 5, 8. The recursive code is elegant. Fib of n returns fib of n minus 1 plus fib of n minus 2. Base cases. Fib of 0 is 0, fib of 1 is 1. Just 3 lines. But notice, there are 2 recursive calls. That changes everything. Call fib of 5. It needs fib of 4 and fib of 3, 2 calls. Fib of 4 needs fib of 3 and fib of 2. Each call branches into 2 more, forming a tree. This is tree recursion. And here's the crucial thing. Fib of 3 appears twice in this tree. Fib of 2 appears 3 times. The same computation happens over and over again. This redundancy is the fundamental problem. The number of calls grows exponentially. Fib of 5 makes 15 calls. Fib of 10 makes about 170. Fib of 30, over 2.5 million. A simple 3-line function can bring your computer to its knees. The tree is just too big, full of redundant work. Count the leaves of the fib of 5 tree, the base case calls. Fib of 1 appears 5 times. Fib of 0 appears 3 times. That's 8 leaves. These base cases are where recursion finally stops, and their count grows exponentially with n. That's what makes tree recursion expensive without optimization. Your turn. How many total function calls happen when computing fib of 5? Count every node in the tree. Pause and think. 15. The fib of 5 tree has 15 nodes, and each node is 1 function call. That's a lot for just the 5th Fibonacci number. 2 recursive calls means exponential growth. Watch for redundant work. That's the key.